Today, I will present semantic understanding of smart contracts, executable operational semantics of Solidity. The success of Bitcoin since 2009 stimulates the development of other blockchain-based applications, such as Ethereum, a second generation of cryptocurrency, which supports the revolutionary idea of smart contracts. A smart contract is a computer program written in a Turing-complete programming language called Solidity, which is stored on a blockchain to achieve certain functionality. Smart contracts benefit from the features of the blockchain in various aspects. For instance, it is not necessary to have an external trusted authority to achieve consensus, and transactions through smart contracts are always traceable and credible. Smart contracts must be verified for multiple reasons. Firstly, due to the decentralized nature of the blockchain, smart contracts are different from programs written in other programming languages. For instance, the storage of each contract instance is located at a permanent address on the blockchain. In this way, each contract instance is a particular execution context, and context switches are possible through external calls. Particularly, delegate call is executed in the context of the caller rather than the recipient, making it possible to modify the caller state. Thus, programming smart contracts is error-prone without a proper understanding of the underlying semantic model. Secondly, verifying smart contracts against vulnerabilities in deployed contracts is crucial for protecting digital assets. One well-known attack on smart contracts is the DAO attack. The attacker exploited the vulnerability associated with fallback functions and raised agency property in the DAO contract, and managed to take $6 million under his control. Finally, unlike traditional software, which can be patched, it is very difficult, if not impossible, to patch a smart contract once it is deployed, due to the very nature of the blockchain. There is a surge of interest in announcing and verifying smart contracts. Some of the existing works conduct verification or security analysis on EVM barcode. For instance, OINT is a symbolic execution engine which targets barcode running on Ethereum virtual machine. In addition, KEVM is the semantic encoding of EVM barcode in the K framework to facilitate the formal verification of smart contracts at barcode level. A set of test oracles is defined in contract further to detect security vulnerabilities at EVM level. Securify translates EVM barcode into a stackless representation in static single assignment form to infer semantic facts for analyzing smart contracts. In other words, the verification or security analysis of smart contracts is based on intermediate languages. For instance, the formalization in AppStar is an intermediate level representation for the equivalence checking of Solidity programs on EVM barcode. In addition, DUs translate Solidity contracts into programs in an abstract language, which are translated into LLVM code to verify smart contracts. Similarly, Solidity programs are translated into Boogie programs to be analyzed in Vercel. To the best of our knowledge, most of the existing works either focus on EVM barcode or translate Solidity contracts into programs in intermediate languages, which are suitable for verifying smart contracts or detecting potential issues in associated verifiers or checkers. We believe that it is necessary and also important to formally define the semantics of Solidity. The first reason is that programmers write and reason about smart contracts at the level of source code. Without the semantics of which, they are required to understand how Solidity programs are compiled into barcode to understand these contracts, which is far from trivial. Secondly, even though Solidity contracts can be transformed into programs in intermediate languages to be analyzed and verified in existing model checkers and verifiers, the equivalence checking of Solidity and the intermediate language considered is crucial to the validity of the verification. For instance, most of the false positives reported in DUs are introduced by the semantic inconsistency of Solidity and the abstract language. Finally, although alternative high-level smart contract languages such as Viper, Bamboo, and Flint have been proposed for safer programming, Solidity is still the most popular language for writing smart contracts. The challenges of developing Solidity semantics lie in two aspects. Firstly, there are insufficient documentations defining or describing the complete features of Solidity. Furthermore, these documentations fail to address corner cases, This requires that the Solidity semantics has to be executable for extensive testing. Another way to understand the semantics is to figure out how Solidity compilers, such as Remix, interpreted by observing the execution behaviors. However, these compilers only capture low-level instructions, which may be inconsistent with the high-level semantics. Therefore, it is necessary to define the correct semantics from the perspective of what it should be to get rid of the misunderstandings introduced by the compilers. The second aspect of the challenges comes from the language features. The decentralized nature of the blockchain makes the Solidity features unique. Furthermore, the blockchain-related features in Solidity, such as fallback functions and transaction-based exception handling features, add to the difficulty of the semantics design, since there are no standard interpretations that can be borrowed from other language semantics to take into account the blockchain context. Apart from uniqueness, Solidity supports a variety of calls, such as high-level and low-level calls, constructors and fallback functions, possibly with error transfer, in different formats of syntax, and exception handling features, such as assert, revert, and require. A uniform mechanism is necessary to construct semantics to make it extensible. Finally, in order to survive in the language evolution, Solidity semantics must be designed from a very general point of view. In this work, we develop an executable operational semantics for Solidity. Firstly, our work is a first approach to our knowledge to a complete executable formal semantics of Solidity constructed directly on the language itself, other than Solidity compilers. Secondly, the proposed semantics provides a formal specification of smart contracts, which solves the specification issues in the existing verification and analysis tools. Thirdly, the proposed semantics allows us to formally define semantic level security properties for verifying smart contracts. Finally, the proposed semantics defines correct and secure high-level execution behaviors of smart contracts to reason about compiler bugs and assist developers in writing secure smart contracts. The proposed Solidity semantics is formalized in the K framework. The K framework is a rewriting logic-based formal executable semantics definition framework. The semantics definitions of various programming languages have been developed using K, such as Java and C, particularly an executable semantics of EVM, the backend language of smart contracts, has been constructed in the K framework. K backends, like the Isabelle theory generator, the model checker, and the deductive verifier, can be utilized to prove properties on the semantics and construct verification tools. A language semantics definition in the K framework consists of three main parts, namely the language syntax, the configuration specified by the developer, and a set of rules constructed based on the syntax and configuration. The syntax of the proposed Solidity semantics is constructed based on the official Solidity documentation. The configuration is designed specifically for Solidity smart contracts. Based on the syntax and the configuration, we formalize the operational rules for the language features with rewriting logic. This is the random configuration of Solidity. In this configuration, there are six main cells in the whole configuration cell T, and they are K, control stacks, contracts, functions, contract instances, and transactions. In the cell K, the source programs called source unit are stored for execution. The cell control stacks contains contract stack, function stack, new stack, and the block stack. The record stack information related to the program execution. In the cell contracts, a set of contract definitions is stored. Each cell contract represents a contract definition and stores the corresponding information. Similarly, the cell function stores a set of function definitions. Each cell function represents a function definition and stores the relevant information. In the cell contract instances, there is a set of contract instances. Each cell contract instance represents a contract instance and records the corresponding information. Transaction information, including gas consumption, is stored in the cell transactions. There are two kinds of transactions for smart contracts, namely new contract instance creations and function calls. Let's start with the semantics of new contract instance creations in Solidity. The semantics rule for creating a new contract instance is shown in new contract instance creation. Creating a new contract instance in Solidity is achieved through the expression new XE, where X is the contract name and E specifies the arguments in the constructor. There are altogether three substeps for this transaction, and there are update state, allocate storage, and init instance. To be specific, update state updates the blockchain states, including the states of contract instances and transactions, and the stack information to indicate that we are in the process of a new contract instance creation. In addition, allocate storage allocates state variables, and init instance deals with initialization issues, such as calling the constructor in the new contract instance. Next, I will present the semantics of function calls in Solidity. Most of the vulnerabilities in smart contracts are associated with function calls, such as reentrancy, the parity volley bug, and exception disorders. Function calls in Solidity are written in a format similar to member access. For instance, target.deposit.value true is a typical function call in Solidity. To be specific, target specifies a recipient instance, and deposit is the function to be called in that instance. Value specifies MSG value as 2. In addition, we can specify other parameters, such as MSG gas and function arguments in the function call. In order to make the semantics of function calls general for all kinds of calls and extensible for different kinds of smart contract languages, a uniform format of function calls is applied to generalize the semantics. The uniform format is function call, ID of caller, ID of recipient, function name, function arguments, MSG information. The semantics rule for function calls based on this format is shown in function call. When it comes to the semantics of function calls in Solidity, the first thing to do is to decompose the member access-like format and transform the call into the one in a uniform format, as shown in decomposed Solidity call. Each decomposed part in Solidity calls is reorganized in function call. The semantics of function calls is designed from a general point of view. Each external function call is regarded as an extension of an internal function call. Whenever there is an external function call, we first switch to the recipient instance, and then call the function in this instance as an internal call. Finally, we switch back to the caller instance. In this way, external function calls can be achieved through internal function calls and switches of contract instances. This mechanism also applies to internal function calls, where the caller instance is the same as a recipient instance. There are three substeps in function call. The first one is to switch to the recipient instance from the caller through switch context. The second is an internal function call. The last one is to return to the caller instance through return context. The semantics rules for function calls apply to all kinds of calls in Solidity, including high-level and low-level calls, constructors, and fallback functions. For instance, if there is no function name specified, or the specified name does not match an existing function in the recipient instance, the first decomposed part in decomposed Solidity call will be the fallback function in the recipient instance. In addition, in the case of delegate call, the recipient instance R is the same as the caller instance C, since the execution takes place in the caller's context. We evaluate the proposed Solidity semantics with the Solidity compiler testset. As for types, the semantics definition in the K framework covers address, bool, string, integers, unsigned integers, and byte. Fix and UFix are not covered because they are not fully supported by Solidity yet. User-defined types, including struct, contract types, and enum, are covered. Mappings, arrays, function types, and address payable are also covered. The semantics associated with functions, such as function definitions and function calls, is fully covered. Furthermore, the semantics of statements is completely covered, except that of inline assembly statements, which are considered to be low-level features accessing EVM, and as part of semantics can be integrated with KEVM. All kinds of expressions in Solidity are covered. The semantics of the event is also covered. The parts of semantics for using for and inheritance are covered with rewriting. For all the parts of cover semantics, they are considered to be correct, since the execution behaviors involved are consistent with the ones in the official Solidity compiler remix. Therefore, the proposed Solidity semantics can be considered to be complete and correct in terms of the supported high-level core features of Solidity. In this work, we introduce an executable operational semantics of Solidity, formalized in the K-framework. The semantics is designed from a general point of view to adapt to the language evolution of smart contracts. Experiment results show that the proposed Solidity semantics has already completely covered the supported high-level core language features specified by the official documentation, and the cover semantics is consistent with the official compiler remix. The semantics facilitates the formal verification of smart contracts and the formal specification of Solidity. Also, it assists developers in writing secure smart contracts and reasoning about compiler bugs. That's all. Thank you.